In calculus, the exponential function that we deal with the most by far is the exponential function e to the x. E to the x is an exponential function with a base of 2.718. That's what e stands for, and it's actually a decimal that never ends. It's actually longer than that, but rounded is about 2.718. So it's exponential growth because the base is bigger than 1. And so because we use this so much, because it shows up so much in nature and in financial math and in biology and physics and what have you, this is the guy primarily that will focus on differentiating, is simply because we run into it more often than any other exponential function. So here we go. In this video, I'm not going to do tons of examples. This one's going to be primarily just to explain why the derivative is what it is. Okay, so here we go, the derivative of e to the x. So I'm not going to give it to you quite yet. We're actually going to figure out what it is. The exponential function has these amazing mathematical properties that are very, very surprising. And one of them will hint as to what this derivative is. All right, so let's go through this here. If I picked a point like the y-intercept of e to the x, so if you plug in 0, e to the 0 is 1. And so if we looked at a y value of 1, just a shot in the dark, if you just looked at this graph here, what does it kind of look like this slope is? Well, to me, it looks about like 45 degrees. If you guessed a slope of about 1 right there, you would be correct. It is a slope of 1. Well, let's keep going. If you picked a y value a little higher, maybe like 2, if you look at the graph, you might notice it's a little steeper there, steeper than 1. So if the y value is 2, any guesses on what you think the slope might be? Well, in fact, it turns out to be exactly 2. If you picked a y value of 3 or 4 or 5, then the slope would match perfectly whatever that y value is. So depending on what your y value is, like 3, the slope would be 3. Same thing is true if you pick smaller y values. So the ones that are way back here, way back here. Now look at that tangent line. Is that tangent line perfectly flat? I don't think so. It's slightly tilted up, which means that the slope would be just bigger than 0. Maybe let's say like a half or something like that. Well, notice, look at the y value too. The y value is just above the x-axis. It would also be a half. So you have this perfect relationship between the y values and the slopes, specifically on this function. This is a very rare function. This is one of the only functions that this happens for. So does this hint at what the derivative would be? Absolutely. The y values are coming from the function e to the x, but the slope, as we well know, comes from the derivative of the function. So if the original function is e to the x, and the derivatives match the original function, then the derivative must be e to the x. And so that's your exponential derivative rule. The derivative of e to the x, turns out, is e to the x. That makes it one of the best derivative rules to remember. It's very easy to remember because the derivative is itself. So from there we can do a couple examples. Let's try these are some very, very easy ones. First up, 5x squared minus e to the x. The derivative would be 10x. This is compatible with all old derivative rules. 10x minus e to the x, because the derivative of e to the x is e to the x again. How about this one? This one has a product rule. The derivative of f would be derivative of the first, 3x squared, times the second, so times e to the x, plus the first, that's x cubed again, times the derivative of the second. Here's the new guy. The derivative of e to the x is again e to the x. So I mean, you're sitting here thinking, man, that's the best derivative rule I've ever heard. And in fact, it is kind of. I mean, it's very straightforward. Now, I might be oversimplifying it a touch, though, because there is something you have to watch out for. The derivative of e to the x is e to the x only if the term is just e to the x. If you have something else, which you often do, this is very, very common. If you have e to the 4x plus 1, his derivative is not e to the 4x plus 1. It's very, very close to that, but we need another rule in conjunction with this basic rule that we're going to look at in the next video. What do we need here? Well, when I look at this, what I'm seeing is composition. I'm seeing layers. The outside is the exponential layer, and the inside is the 4x plus 1. So what we need is the chain rule. You might remember that rule from a few videos back. So it turns out we'll have to use the chain rule in conjunction with the exponential rule. And just so this video doesn't get too long, we're going to stop this video right now and do that one in a separate video.